Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on ring theory, lecture number 11, in which I will give the details concept of integral domain. Let R be a non-empty set with binary composition, addition and multiplication, and let this algebraic structure is a ring. Therefore, R with binary composition addition is an abelian group. This is number one. Number two, R with binary composition multiplication is a semi-group. Number three, distributive law holds. That is, A multiply B plus C equal to A multiply B plus A multiply C, and B plus C multiply A equal to B multiply A plus C multiply A for all A, B, C belong to R. Here in number 2 we see that the non-empty set R with binary composition multiplication is a semi-group. That means number 1 closure law, number 2 associative law. If we add with this, number C, having unity element, number D, commutative. That means if A, B belong to R, then A multiply B equal to B multiply A. And one more property, R with binary composition addition and multiplication is without zero division. Then for these properties, extra properties of ring, the ring will be changed into integral domain. Then we may say that a non-trivial ring R with unity element, commutative, and is without zero divisor, then this non-trivial ring is called integral domain. Now we write the definition of integral domain. Definition of integral domain. A non-trivial ring with unity, commutative, and contains no divisor of zero is called an integral domain. Now we see some example such that they are integral domain or not. Example 1. The ring Z be the set of integers with binary composition, addition and multiplication. This Q, set of rational numbers with binary composition, addition and multiplication. R, the set of real numbers with binary composition, addition and multiplication are integral domain. Since we know that these all theories are ring. Now we see that unity 1 belongs to Z, also 1 belongs to Q, means 1 is an integer, 1 is a rational number, and 1 is a real number. 1 unity belongs to Z, Q and R. Commutativity, A multiply B equal to B multiply A for all AB belong to Z or Q or R. Having no divisor of 0, if A not equal to 0, B not equal to 0, A, B may be integer or rational number or real number, then A multiply B not equal to 0. That means these do not contain divisor of 0. Then these three will be integral domain. Here example 2. 2Z with binary composition, addition and multiplication. Z be the set of integers. Since 1 belongs to Z, if we multiply all the members of Z by 2, 1 changes to 2. 1 multiply 2 equal to 2. So we do not get a unity element in 2Z. So this is a commutative ring without unity, and also it does not contain divisor of 0. Only for lacking of one property, unity, this ring is not an integral domain. Example 3. Z5 with binary composition, addition and multiplication is a commutative ring with unity, and it contains no divisor of 0. If we take two non-zero elements of Z5 and if we multiply, we do not get 0 element. So Z5 with binary composition, addition and multiplication is an integral domain. Next example. Example 4. Z6 with binary composition, addition and multiplication is a commutative ring having unity, and it contains divisor of 0. Since 2 bar, 3 bar belong to Z6 and 2 bar multiply 3 bar equal to 6 bar, that is 0 bar. So 2 bar not equal to 0, 3 bar not equal to 0, two elements of Z6, non-zero element of Z6, but their product is a 0 element. So Z6 contains divisor of 0. So Z6 is not an integral domain. Example 5. The ring MNZ means n by n matrices, collection of n by n matrices whose entities are integers. Since it is a ring having unity element, but it is not commutative ring, because matrix multiplication is not commutative, and only for this ring is not an integral domain. Now we prove a theorem. Theorem is, let D be an integral domain, then non-zero elements of D form a commutative semigroup under multiplication. Now we prove this. Given that D be an integral domain, therefore D will be commutative ring with unity and contains no divisor of 0. Let D star equal to D minus a set containing 0 element. Therefore, D star contains non-zero elements of D. Therefore, AB belong to D star implies that A not equal to 0 element, B not equal to 0 element, and AB belong to D. Means AB are non-zero element of D. AB belong to D implies that A multiply B belong to D. Since D with binary composition multiplication is semi-group, because D is an integral domain, so D is a ring and each ring is semi-group with binary composition multiplication. Again, since D contains no divisor of 0, therefore A not equal to 0, B not equal to 0 implies that A multiply B not equal to 0. A multiply B belongs to D and A multiply B not equal to 0, as A not equal to 0, B not equal to 0 means product of two non-zero elements of D is an element of D and that element is non-zero element, implies that A multiply B belongs to D star. Therefore, AB belong to D star implies that A multiply B belongs to D star. Therefore, D star with binary composition multiplication holds the closure property. Number 1, this. Let A, B, C belong to D star and D star is subset of D, implies that A, B, C belong to D. Since D is associative, therefore A multiply B multiply C equal to A multiply B multiply C, bracket change, since D is associative. D is an integral domain, so D is a ring, so D is associative with binary composition multiplication. Therefore, D star is associative. D star with binary composition multiplication is associative. This is number 2. Let AB belong to D star implies that AB belong to D. Since D is commutative, therefore A multiply B equal to B multiply A, implies that D star with binary composition multiplication is commutative. This is number 3. From 1, 2 and 3. From 1 and 2, we get that D star with binary composition multiplication is semigroup. And here we see commutative property. Therefore, from 1, 2 and 3, we get that D star with binary composition multiplication is a commutative semigroup. Proved. Now we prove the next theorem. Next theorem is a commutative ring R with unity is an integral domain if and only if for every non-zero element A in R, A multiply U equal to A multiply V implies that U equal to V, U, V are elements of R. Now we prove this. Since given that R is a commutative ring with unity and A belongs to R such that A not equal to 0 means A is non-zero element, and also AU equal to AV implies that U equal to V, U, V are elements of R. Let V equal to 0 element, then AU equal to AV implies that U equal to V, UV belong to R implies that A multiply U equal to A multiply 0 implies that here in place of V 0, U equal to 0, U 0 belong to R implies that A multiply U, here A is non-zero element and 0 is 0 element, product of any non-zero element with 0 element is 0, this is 0 implies that U equal to 0. So for A not equal to 0, AU equal to 0 implies that U equal to 0. Therefore, A is not a left divisor of 0. Since R is commutative, so A is not a right divisor of 0. Therefore, A not equal to 0 is not a divisor of 0. Since A is an arbitrary non-zero element of R and A is not divisor of 0, therefore R is an integral domain. Since already given that R is commutative with unity, and here we get R does not contain divisor of 0, that means R is without divisor of 0, means R contains no divisor of 0, therefore R is an integral domain. Proved. This is necessary part. Conversely, let R is an integral domain. Now A belongs to R and A not equal to 0. Then A multiply U equal to A multiply V, U V belong to R, integral domain. Implies that A multiply U plus minus A multiply V equal to A multiply V plus minus A multiply V, implies that A multiply U minus V, distributive law. By distributive law, here 0 element, A multiply V is an element of ring R, means integral domain R, and this is the inverse, additive inverse. Implies that U minus V equal to 0. Since R is an integral domain, so R contains no divisor of 0. Implies that U equal to V. Proved. Sufficient part proved. That is, A multiply U equal to A multiply V implies that U equal to V. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.